And okay. Hi guys. So probably this is the first time for you guys to attend our seminar, right? And it's our great pleasure that we have Dr. Dongfang Liu to give us his talk about his recent research. But probably you guys don't know me. I'm assistant professor in the Center of Information Science, and just this time is first time we have the speaker in this year. In the past, we have quite a lot of times we have a speaker, but due to COVID-19, we stopped a little bit while. And this is the first time in these 2 years we have in-person seminars. Dr. Dongfang Liu has dedicated his research on effort to explore the innovation opportunities for interdisciplinary research to address real-world challenges with social relevance using artificial intelligence and machine learning. He has studied domains. Span from autonomous driving, mobile agents, smart translation to geospatial computing. He has published quite a lot of papers on top conferences like Actual, ICCV, CVPR, AAAI, those conferences. You guys should target as well during your PhD research. An ongoing project are autonomous driving and video instant segmentation. And since most of you guys are PhD students, and Dr. Liu grad from Purdue University with a PhD in visual computing, right?
Computer graphics.
Computer graphics. Okay. Okay. And actually, if you guys still feel suffer to take classes and taking a PhD, and Dr. Liu has actually taken two doctor degrees beforehand. So you should take him as an example in your education. And so don't think about PhD too difficult. Someone is here taking two doctor degrees. Okay.
Yeah, thank you.
Liu, please go ahead.
Okay. Thank you, Dr. Liu, for these kind introductions. I guess I can take over now. So the talk, the title for my talk today is a video detection, segmentation, and the navigation for the autonomous agent. And primarily we'll focus on the visual-based perception for the autonomous system. And obviously this is quite important. Speaker. Okay, let me do this. Hello. And you guys hear? Okay, thank you. So obviously this is quite important research because for a robotic system, they need to build the environment awareness to support the high level control or decision makings. And we can use detection as an example. For instance, our autonomous driving car, they need the detection, has the capacity of a detection to understand other road users or avoid obstacles, or they want to have some kind of control to support their, have some kind of perception to support their control. But the one thing I want to clarify at the very beginning that currently in the industry, people intend to use multiple sensor measurement instead of like using camera sensor. I think right now, SOTA is one of the isolated case only use visions. But for other bigger companies, they intend to use multiple sensor to build up the sensor fusion, so they can have a better system like security and guarantee. But in our academia, can you guys hear me? Okay, because it's okay. Okay. So in current academia, I think vision-based AI task is quite dynamic and active because you look at some of the leading AI conference. For instance, CVPR, ECCV, and ICCV that are it's kind of purely focused on the vision task. Well, versus we have AAAI and LIPS. They're also very good conference, especially I think LIPS is one of the top conference right now. Large proportion of the publication also focus on the vision side. In the past few years, I was able to develop some research portfolio in some of these conferences. So today, we will talk about some of the project I delivered in the past few years. And for the first two projects, we'll talk about the video video detection and video instant segmentations. And we will talk about some of the background information regarding the two tasks. And then we'll talk about some of the limitation for the SOTA. SOTA, by the way, means state of art method. And how we come up with the idea to address some of the limitation of the SOTA method and push the limits or boundaries. After that, we'll talk about the video navigations. So we will learn how to only use vision to resolve the problem of the indoor navigations. And of course, we cannot use any actual knowledge, for instance, GPS or prior map or something like that. And the reason I choose these three projects because they are highly interrelated and they are quite important for the operation for our mobile robot. So the first project, video object detection. So the first question we want to ask, like why we want to talk about video object detection, because it seems like we have tons of research focused on the object detection domain. And here we kind of have a quick demonstration why. So in the first row, if we feed this video frame into image detector, FCOS is by far state of art. It's coming out last year from the CPR. You can see that because of the whole frame is kind of compromised, it's very blurry. So it's fairly hard for the image detector to understand, oh, this is coming out, to perform detections. And versus at the lower level, it's our method, it's a method trainer for the video domain. We can see that we have a nice location of the bounding box as well as the accurate classification for the class. So the thing is, at the video domain, we will come across many, example like that. We have compromised frame caused by defocus, motion blur, something like that. So we definitely want to find a new solution for this new domain. But before we dive into technical details about video object detection, let's revisit what's detection at the image level. So we have this nice RGB input, this little cat. So the first step is that we have this CN backbone. Hope you guys understand what CN is. Backbone to extract features. So once we extract features, following that, we have the detection head. That's a very common term, we can call it detection head. So the function of the detection head to do two things. They have the box level aggression, so provide us localization of the object. Another thing that also can provide the labels. For instance, here it's a cat versus it's a dog. So this whole pipeline is pretty simple. But at the video domain, I think the foundational difference versus the data from the image level is that we have a lot of temporal informations. So for instance, here, cross frames, we have this red truck stay on the appear and stay on the frame for quite a long time. So one thing we can think about is that can we leverage the temporal information nicely to improve the detection of the video domain? And that's actually the philosophy right now, majority of the state-of-the-art method using. And one thing we think about is that can we use temporal information to increase the pixel level representations? So basically, we have temporal information, for instance, T minus I. We extract the features, and can we propagate the feature from a previous moment to the current moment? And we can do that by like simple feature concatenations. So the key problem here is how we can model the movement. So a lot of methods, come up different idea to do that. So essentially, for the learning-based solution is that we can use the technique called the optical flow, or people just call it simple for like a flownet, to model the spatial change cross frames. So we can build up the correspondence from the previous moment to the current moment for the same geospatial location on the image frame to check the movement of the pixel. And on the right, we have the output of the flow field. What we call flow field is output of the flownet. We can see that we have different color, we have different shade. So the shade of the output means so darker shade means larger movement. The lighter shade, it means small movement. This is very intuitive. Another thing we can pay attention is the color. So we have a blue, we have red. So different color actually means the directions. So essentially for the output for the optical flow has two dimensions. One dimension is a scale, like how large the offset is. Another thing is like what kind of direction we have. So with this help, with the help of the optical flow, people can propagate the feature from previous moment to the current moment by simple concatenations, and then feed into the detection head. We can see the obvious improvement. So with feature propagation, we have more accurate detection. We detect more object on the frame versus without using feature propagation or aggregation, the detection quantity is fairly low, and obviously we're missing few objects as well. So So what kind of problem, our method try to address? So one thing we think about is, hey, we try to propagate a feature from the previous moment to the current moment. That's simple enough. But another intuition actually guide our research is that we think about, hey, if we think about temporal feature, if the temporal feature has high similarity to the current frame, we think, hey, this might be, offer more value, right? If we compare the temporal frame versus current frame, and we find out there's a few pattern or representation similarity, we think, hey, probably this, temporal feature offer less values. So in order to do that, we design a little module called adaptive weight. So this thing will really control the contribution of the temporal features. And so in order to propagate our feature from the previous moment to the current moment, we add the a little weight here. If we visualize this process, the improvement is obvious. So if you look, pay attention to the T moment. So at the lower row, that's a feature map. And we also visualize a response, the activation response for the feature map. We can see that the original card class is fairly null, which means that if we feed this feature map into our detection head, we probably end up with a poor detection or weak detections. And the solution is that we add up from T-3 to T-1, and using adaptive weight and concatenating together, we can see that activation for the card class is improved, which means that, hey, this is a better feature. So we feed into the same detection network, we can improve the detection result. But so why are we doing this? We identify a few questions, actually two problems here. So the first problem is that, so we do have this adaptive way to model the kind of temporal feature versus current feature, but for the local feature of the temporal feature, we don't have explicit modeling on that. And obviously we want to propagate a feature only the valuable proportion of that rather than, hey, we want to propagate the whole, feature from the, temporal feature from previous moment to the current moment. And this obviously can save us a lot of computation budget. Another thing is that if you look at the visualization process, we use T-3 to T-1. And if you look at the literature, you can find people use 3, 4, 5, 7, and try to argue which range is better. And obviously this is quite dumb, right? Because we don't like fixed number. So to address this, we come up idea of the blender. So with this, we want to do two things. The first thing is that we want to have a flexible range. We want our model to tell us, hey, what's the range we want to use? So this is a global reasoning. Where's my mouse? Okay. So global reasoning will help us to identify the relationship between the temporal feature versus current feature, and help us to dynamically choose useful features, only useful features for the next step propagations. And also we want to model the local features. So what we call is local CDC. So instead of using the whole feature map from temporal features, we only want to identify, if you look at the output, we only want to identify part of this. For instance, for detection per se, is that we want to focus on the region of interest. So what's the region of interest? For autonomous driving car, as an example, will be pedestrians or cars versus some other things, for instance, vegetations or some event features. So by doing this, we model the local feature and also we model the global reasoning. And the third module, what we call is the blender. So by blender, we just simply, using the operation of the multiplications. So doing this, we kind of create an attention mechanism. So our propagation actually has more meaningful representations. So if we look at the result, so some of the challenging cases we categorize such as defocus, motion blur, and weird pose. Weird pose is kind of funny name. I'll come back for that. So for the defocus, we can see that again. So FCUS is by far state of art. If you guys want to working on the detection, especially at the image level, you want to check out this literature. It's a really powerful backbone. Sorry, very powerful baseline. So we can see that it's very difficult for the FCUS to perform any detection on the compromised video frame. And at the second row, FGFA coming out, I would say like 3 years ago. But still, before the time our method come out, it's still like by far state of art method. It's very strong backbone oh gosh, baseline, sorry. You can see that the detection result is fairly poor because the bounding box is very large. Versus our method, we can see that we can predict the bounding box location nicely to contain the target. And also, so for the weird pose, I promise I'll come back, is that we observe, especially at the video domain, so many interesting scenario I'll come across is that when the object is coming too close to the camera lens, and kind of losing the global structure of the instance. So it's pretty hard for the the model to understand what is it saying. For instance, here we understand this is boss because for our experience, we saw the whole image of the boss, and also we see the local image of the boss. We can build a connection between the local and the global kind of correspondence. But for the image level detectors, they don't have this knowledge. So when we're training, they don't have too much exposure for the weird pose learning example. So it's really hard for them to understand what's going on here. Versus using our method, we can predict the light bounding box of the target with the accurate class label. Okay, so that's for the first project. So the second project I want to talk about is video instance segmentation. And obviously this is incremental task for the previous one because we're moving from the prediction, moving from the box level prediction to more accurate pixel level prediction. And in the domain of computer vision, we have a few segmentation tasks, and we'll talk about that before we move forward to the main task we're going to focus today. The first one is a semantic segmentation. So we have pixel level prediction, but somehow we care more about the same class, the same instance class or the same instance category. So if we look at the vehicle or pedestrian, especially for pedestrian like standing together, we don't have too much boundary description, right? Because we care more about the same class, the same category. Well, versus instance segmentation, aside from the pixel level prediction, so each individual instance has its own color mask. We also have light prediction of the boundary. So even for the same class or same instance, they have their own color mask. They have the light description of the boundary and edges. And the focus of our today is a video instance segmentation. So this is a direct extension from the instance levels, but we can see that there's some difference. So per frame, we have a bounding box, and we also have a segmentation for the individual instance using different color to represent different instance. But cross frames, we also have, if we have the same instance appear on the frame, we use the same color encodings. So this is really give us a very intuitive information that this is the same instance cross frames. Okay, so we understand what is video instance segmentation. Let's talk about the limitation for the SOTA method. So before our method coming out, the major problem for the SOTA method is that it's actually a two-stage framework. And the majority of the work based on a seminar instance segmentation task called mask RCN by simply adding a tracking branch. So mask RCN doesn't have a tracking branch. It's only like an image level segmentation. And it's a two-stage because they have this regional proposal generation module here. And based on that, they need to predict the detection, segmentation, and the trackings. And obviously, this is a tedious process because we're talking about two-stage. And our goal is, hey, can we move the two-stage to one-stage? It's more compact one-stage solutions. And another problem we want to address because of the two-stage method is that it has so many like redundant proposal representation because earlier for the regional proposal network, for the same region of interest, for instance, we have this, for instance, this 4A plane soccer. For the same region of interest, we have to use the network, we have to predict the number of the candidate proposal around that region of interest because we don't know which proposal will be eventually be used as the final predictions. So this is, as I said, it's redundant because for detection, segmentation, and tracking, they have to encode repeatedly in the area to use a feature to kind of differentiate the foreground versus background. So for the same region of interest, there's a tons of operation because of that. And one significant drawback for this proposal-based method is that if the video frame has increasing number of instances appear on the video frame, the computation budget will increase drastically. And the third problem we want to address is RIU feature restrictions, because we're talking about the proposal operations. All the proposal have to be resized to sometimes it will depend on how you play with the parameter. Will be sometimes, for instance, like a 14 by 14 or sometimes 28 by 28. So this is problematic simply because if you have a large instance on the video frame, we have small instance on the video frame, we all treat them equally with the same size. So this is unfair because large instance, we have to retain a large resolution to kind of keep the nice description of the boundary, versus a small instance, we don't even need much information for the boundaries. So this will cause a problem to prevent the two-stage method to have a further improvement for the performance. And we can look at some of the example here. So lower level here is we call it mask track RCN. It's a two-stage method, state of art, and we have two challenging cases. So first one is we have a spacecraft, and behind the spacecraft we have a hanger. And I can tell you that the two color for the hanger and the spacecraft, the colors are similar. So it's all like an ivory white. And because of that, the two-stage method cannot segment out the background, the hanger background with the foreground like a spacecraft. If you zoom in, you can see the quantities, the prediction quantities are fairly known. Excuse me. Versus our method, we can segment the spacecraft from the background nicely. Another problem is occlusion, which is very common in video frame, like what I'm looking at you guys right now. We have so many occlusion. We have some people sitting in front with some students sitting at the behind. And here the example is that we have a deer, like I think is sitting or maybe laying behind this tree. Aside the fact that the trunk of the tree has a similar color and pattern of the deer, because the deer is kind of a dark brownish color. Another significant problem is that because of occlusion, it causes some irregular shape of the deer. And because of the irregular shape, it's really hard for the two-stage method to segment out the instance. So we can see that this thing is a deer, some part of the tree belongs to a deer, and obviously this is wrong. Okay, so to address this problem, we propose a one-stage framework, what do we call it, SGLAD. So on the left, we just use a very standardized CN backbone. We use FPN. So FPN short for Pyramid Feature Network. So with that, we have this multi-scale representation. But the key contribution is on the right. So that's our key architecture. So we have our detection, segmentation, and tracking, or directly operate on the input features, extract a feature from the CNN. And so we basically like a proposal free. We don't have any middle stage, like we involve any proposal. So this, so with this, it's really give us the immediate benefit we talked about earlier, that two-stage method, they have to use a proposal or increase the computation cost with the number of instances appear on the frame. While using our method, we don't have any proposal, so we are proposal free. We don't have to deal with the problem like if we have 10 people appear on the video frame versus 1 people, the computation cost will increase drastically. Well, this is another case for us. And another significant novelty for us, we promised to address earlier, is that we can segment out irregular shape and with a very blurry background nicely from the foreground out of the blurry backgrounds. And here we can see that this goldfish, the shape is pretty irregular. If you look at the goldfish we segment out. So the reason we can achieve this, because we have this mask modules, which we have 2 Sept modules. The first module we have is a base mask. So instead of like perform the prediction, the segmentation prediction on the whole region of interest, we divide the area, divide the region of interest area into small boxes. So, and we perform prediction on the individual area of the boxes instead of like we perform the segmentation on the whole region of interest. And associated with that, we have the attention module. So attention module is that we also divide the region of area with the same number of the subregions. So for each subregions here, we have corresponding attention score for each corresponding area here on the base mass. And for that, we just use a simple operation like adding the score, not adding, like multiply the two score together and resemble a staying mask and following that by a nonlinearity module. So we can have more representation, nonlinear representations, and to achieve the capacity to segment out irregular shape. And again, so you can see it if you look at the goldfish, some of the shape is pretty hard to segment out, but the result is fairly good. And here's some examples. So for the skydiving, again, we compare our method with a two-stage mass truck RCN. Our performance, our segmentation performance is obviously better because this might be too small, but I can tell you this is another person's hands. So this thing is belong to this gentleman, but it's not. So we can, and for our method, we can segment this hand, which is fairly tiny, nicely. And for the second example, the tiger example is more obvious. So we have two tiger playing, like two baby tiger playing. And this kind of like a blending, like a color and shape is pretty similar. For the two-stage method, they cannot segment out the two tigers because they're just getting too close to each other. Well, we can segment out the tiger, the two tiger, even for this tiger, even without hands, only have the butt side nicely. The third example is tracking. So again, remember we're talking about the occlusion can cause some confusion for the segmentation. Because of the confusion for the segmentation, we cause some problem for the tracking as well. So for the baseline method, we can see that starting from the third frame, the this zebra start to change color. Remember we're talking about for the same instance cross frame, they need to have the same color encoding, so same mask color. But because of this, we understand, oh, he thinks this is a real thing, which is obviously wrong. And versus our method, we can segment, you know, the zebra at the front and also tiny zebra at the backgrounds nicely here. In the next row, we present some bad examples from our model. So we can see that from starting the first three frame here, we kind of failed to segment the cell. This is a baby cell. It's fairly dark, but this is a baby cell. And we did some analysis for this reason is that for the training data set we use, so for the cell category is highly underrepresented. For the other categories, for zebra, tiger, or human, generally the training example, learning example will be like more than 1,000. Well, for the cells, only have like a few hundred. I think it's close to 200. So you really can see the difference between the data gap between these two different categories. And this is I think it's a good takeaway for you guys that when you guys train your own models, be careful about the data you guys are using, because if we're dealing with unbalanced data, sometimes people have call this like a long tail. Long tail means like we have a high representation with certain categories, where at the end we have a few learning examples for certain categories, and the model will tend to learn more representation on this side versus this side. Will cause some confusions when they use your model. And here, I have a little demo for you guys. So our method can actually run on time, use a proper backbone. We can see that we can segment the irregular shape nicely. And for the human inverse, we can segment now pretty good from the background. Okay, so I guess this is a second project. So the last project I will talk about is video navigations. And obviously this is also a challenging task because we focus on the indoor settings. At the indoor environment, we don't have GPS. We don't have too much other knowledge. But alternatively, I think some bigger groups, they can use a Bitcoin sensor, very expensive. You can Google quite expensive device. And you have to place like every color, majority of the color of the inside the room so they can triangulate the location of the robot. But this is obviously very tedious process. And other people can build up the whole map for the robot to understand, but obviously we don't like that because we want to use vision to resolve this problem, simply because camera sensor is very common sensor on robot. So this is very general solutions. But another thing I want to talk about is that, so this method was proposed to solve the problem of indoor application, but it can also be used for outdoor, simply because at the outdoor environment, I don't know how many of you like went to New York or maybe bigger city like Chicago. Sometimes at the indoor, like an inner city drive can be very confusing because they will put you at the wrong road when you have like a tall buildings or vegetation block the GPS. So this can be also used for the outdoor navigation as well. But for the using vision to resolve the navigation is not a new thing. But traditionally, I think the major problem for the learning-based solution is that they try to use the pixel level information directly to predict the action. So they treat the deep learning network as a black box and treat it as a scratch end to end. So I think the major problem is that the direct optimization from the pixel to action sometimes will capture some unreliable dependencies, resulting in suboptimal policy as well as long training schedule, because simply you have to figure out like for each individual pixel what this means for our actions. So we struggle to understand, where's the target, how far we need to go, and what kind of pathway we can go. So a natural question for us is that instead of like using low-level features, can we use a high-level representation from different modalities, for instance, from those modalities to empower the navigation process? And if you think about our daily experience, for instance, like in this room, if we want to go, for instance, go to that chair over there, probably what we want to do is, first of all, identify where's the target, right? And then from your place of origin, you want to figure out like what kind of pathway you guys can go and how far you guys can go. So with this intuition, we develop a multimodal fusion kind of network to leverage some of the high-level representation modality we talked about earlier, for instance, detection, segmentation, and depth estimation. So with that information, we resolve this problem, which is like, where is the target? And can we identify the target? Of course, using object detection, we can look around, the robot can look around and identify the target. And also how far we need to go to the target and what kind of walkable area, because segmentation, remember segmentation has a pixel level prediction. So we understand, oh, this is floor versus this is wall. And we have some common items at the indoor environment. We have chair and some other things. So this is our framework. So essentially, we're adding one interesting module, which is what we call is text, voice to text modules. So we can convert our voice into the text features and can gather the information into our models. And essentially, the component is here for our model. So we have visual encoders to encode the domain features for detection, segmentation, and navigation, and depth estimation. And all the features are feed into the multiprocessors to identify the feature saliency. And following that, just have a simple concatenation to concat all the useful features together. And this is basically our encoding part. And following the encoding part, we have decoding part. We have long-term, short-term memory. This is very standardized implementation for the robot, like reinforced learning robot common generations. And following that, we have a dense estimations. So with this, the whole pipeline, we can predict the policy, for instance, moving forward to left or to right, where certain degrade. But one caveat for the feature aggregation cross modality is that sometimes certain representation will become dominant, and we don't like that, simply because we want to strategically select the feature, because if we find some features are redundant, won't do too much help for your policy generation. You want to find a feature which is complementary to each other. This will provide more values for your policy learnings. So with that said, we kind of devise a little module called the similarity measurement to have the measure the similarity score across different domain. So we can say, hey, this part of module has more similarity to that module. So combine them together, we use a certain way or regularization to polish the contribution of that modules, and before we concatenate them together. And eventually we evaluate our method on AI to SOAR benchmark. It's a benchmark everybody uses right now, using two metrics. So the first one is successful rate. The second one is called SPL. So successful rate is to evaluate for your robot within episode if your robot can complete the task. For instance, grab the cap. If your robot can go to the desk and grab the cap for you, or if your robot can say, hey, go to the fridge, if your robot can go to the fridge. And SPL to evaluate how efficient the robot can complete the task. Obviously, this is also quite important as well, because using 10 steps is obviously better than using 100 steps. And you can see from the metrics that we outperform at that time, because this thing, I trust, has been changed a lot. We outperformed the latest state of art method at that time again as well. Let's see a little demo here. So at the very beginning, we can just give order to the mobile agent. This one is go to the garbage can. Whoops. So the baseline method we use is SAVN. So SAVN is a very strong baseline coming out at CVPR 2019. So basically, he only used the lower level features. So it's very interesting comparison of SAVN versus our method. So one interesting thing, we can find for the SAVN is that his movement is more random. So when they're getting close to the target area, he kind of getting confused and working around without too much sense of the target. If you look at our method, it's good. It's very interesting to compare the behavior between the two methods. So with this high level information, we have segmentation, we have detection. The behavior for our model is that our agent can directly, once he identifies the target, he can directly go to that area with a little bit like moving around in case he thinks there's a kind of an obstacle on the trajectory. So it's more goal driven versus the SAVN. Okay, so this reference for the some of the work we talked about today. Yeah, I guess that's pretty much it. And then now I'm open up to questions if you guys have any.
I have a question. You could go back to slide 10.
Okay. This 10, oh, no, it's A.
Actually, I have a question. So,
okay.
I'm assuming this, when you deploy your model, it has to like fulfill certain real-time requirements, right?
Which model? Which model you're talking about?
your model for like video instance segmentation. So if you're trying to use it on a robot that is trying to get somewhere to a certain object, you would have to like detect obstacles in real time, right?
Right.
So is there any way you measure like these real-time requirements, or like how fast the boxes are appearing as you're moving through a live video?
Yeah, we can definitely track the time. But in general, so for the vision task, in general is that we kind of record all the data together. So in testing, we can test how fast per frame our model can perform their predictions. And of course, you can also use the trained model to run on time for the, for instance, like at a local area, you want to run on time to see how effective it can perform his job. But in general, back to your question is that to do testing, we connect the data ahead of time because we need to allocate the data. So you can, when you test your data, you can compare, aside from the time you're talking about, like a runtime you're talking about, you also want to compare how the performance, the code performance, for instance, like for the pixel level prediction, if the mask is actually follow on the target instance and all that. Did I answer your question? So per frame, we can calculate how fast it can, compute the, for instance, videos.
Yeah, like so a lot of real-time object detectors, they use a certain metric called boxes per frame. So I don't know if you guys use that or maybe some other metric for real-time performance. For the
real-time performance, box per frame, I don't familiar with that terminology, but back to your question, to evaluate the inference time is that we connect data ahead of time. Before you implement that thing into practice, you want to connect data ahead of time as your testing data, and you can evaluate how fast your model can run on time and calculate the per frame calculation speed and all that. And purpose for that is that you want to compare the ground truth versus the inference of your model and to evaluate the performance of your model as well, because runtime is one metric. Another, we care more about the accuracy.
Real time, not runtime. Like real time detection.
Mm-hmm.
Like how fast the boxes are showing up for when you see unseen data, unseen frames.
Okay.
Like how fast? But yeah, I guess I got an idea.
Yeah. Right. And so another thing I want to address here is that it really depends on what kind of computation resources you use. For instance, if you want to run on CPU versus you want to run on GPU, even you test on like a real time, you get a different result. So we care more about how actually your model perform versus runtime, because it really depends on the computation resources you have. Hope that makes sense to you. Yes.
Can you go back to previous slide? Before this, like
This
showed a flownet architecture.
this one?
No, there is a flownet. Kind of, we use a flownet to find out the optimal flow.
Okay, this one.
Yeah. So basically, my question was like, in optical flow, we assume that the intensity of the two frames is kind of similar. Like the features that we are trying to detect in both the frames will have similar intensity. But like if we go along the time, like in the time axis, the intensity may vary, right? So my question is that is flownet robust to that kind of differences, and can it actually predict like when the what do you call it, like the intensity in light variations,
Okay, so I guess the question is like if so are you talking about like the range? Like you're talking about like if the range is too long, sometimes the flow network will not predict the actual movement.
Yeah,
because, for instance, like one drastic thing will be like this vehicle already out of a frame and you're still using that information. Yes, that's a good question. So that's why we want to have the measurement of the temporal range. Otherwise, we cannot decide like what kind of range we want to use. So even using so even using like a 3 frame to maybe 10 frames, the dangerous situation you just described may not occur because 3 frames is very fast, right? But I totally understand your question. Sometimes we'll encounter the problem that the region of interest already move out of the frame, which causes a very big problem. That's why we need to model the relation between cross frames, the temporal reasoning, so we don't select something. For instance, you just described that the region of interest already move out of frame, which definitely offer nothing for us.
I'm trying to understand how, like, there are traditional methods to finding optical flow, and there is flownet. So I'm trying to find out the difference, like how is it different from the traditional classical methods of finding out optical flow?
Oh, we use optical flow as a tool. We didn't for the algorithm perspective, we didn't implement something new for the algorithm of the optical flow algorithm. We just use the output information to model our feature propagation. That makes sense?
Yeah.
Okay.
Okay. I have a second question.
Sure. Yeah.
About video navigation. So can you go back to that?
Sure. Yeah.
Yeah. So my question was like, how do you basically position the robot in an environment? Like, do you use an IMU or do you use the environment itself to locate the localize the robot in that environment?
Can you elaborate, please?
Like like you have to localize your robot, right? So
we don't localize our robot. Okay, so yeah, this part I probably need to reiterate some of the things I described. So at the indoor environment or maybe even outdoor environment, visual localization generally can be categorized with 2 major fields. One thing is that you designate the item you want to search. So that's one task. Another task is we don't give you any items or interesting items. Your job is to basically search around for the whole environment and build a map. And for this task, we kind of fall into the first category is that we give you an item ahead of time, and your job is to identify the item. Where's the item? Does that make sense? So he doesn't have to know the localization. He basically have to do is search around, find the item, move to the item.
But in that video, you showed that it was going ahead, moving ahead, then it was taking a right and left. So for that to happen, the robot has to, like, the algorithm has to know if it's going ahead or taking a right. And so that's what I was thinking, like, how are you doing that?
Right. We remember we talked about this module. We have long-term, short-term memory. So it's kind of memorize your step, like previous step or historical step. So you can like build up your actions one step at a time and moving towards that destiny. That makes sense?
Yeah. Okay. So basically, it knows where it is. Like previously, in like there is a what do you call that? You're creating a memory map of the object itself in the environment. So is that how it's happening? I'm not sure.
He doesn't actually recall the environment memory. He was recording the action, his previous actions he has performed, and how this action may generate some kind of reward for his movement towards a destiny. And for instance, on the trajectory, identifying this is target, and he also has a sense of the distance, right? And he wants to move towards that target. So one kind of reward is that we're moving closer rather than we're moving further away. Does that make sense?
Yeah.
Okay. And the beauty of deep learning is that some of the things you describe is we don't have to explicit model something like where we are. Why we're doing this is that we put into the network and we have those parameters to learn or capture the pixel level kind of representation to the higher level kind of action we have. And we do all that in the training step. We have the award function that award each of the step. If this action is beneficial for your final target or final your final goal. And our final goal is the trash can. We move to the trash can. Okay, hope this makes sense to you. Yeah, yes, sir.
So with the linear navigation framework that you have here, so you have input that's from a single camera source right now.
Yes.
So to what extent do you think that this may be extensible to a robot system that would have, say, multiple cameras for navigation?
Okay, so before I answer you this, can you tell me what's your rationale you wanted to, for instance, like a stereo cameras? What do you think is the benefit of using like a stereo cameras?
So, I mean, the idea, well, there would be the potential of maybe some additional feature encoding by having depth information, in addition to just having with multiple cameras being able to, I guess, with the existing segmentation framework, essentially just having an expanded field of view as well. Okay, yeah, that's a super smart observation for the depth thing. So obviously, with the stereo cameras, we can easily to get the depth estimation, and for us, we have to pre-train to get the depth sense of the depth. So that's definitely a good thing. But the drawback is that using stereo cameras, we have to we introduce the problem of calibrations, because we use two eyes, and we have to calibrate like a pixel to the depth, and sometimes it's extra work. So using monocular camera is just easier, I guess. That's a major rationale. It really depends on what kind of task we're dealing with. I guess there's some trade-off, some kind of trade-off. But the one obvious benefit, just you could describe, is that using stereo cameras, it's very easy to model the depths. So yeah.
So I'm actually thinking about the other one, something like
10, right? Okay, let me go back to 10.
So here you are trying to exploring the feature similarity, and if I see you are drawing a graph, are you really using the graph network, or somehow you are just
This is not a graph. This is not a graph. It's not GDD. It's not a GDD. It's just modeling of the feature, like a temporal feature. We didn't use a GDD. Yeah. Which is purely computation of the features, similarity and all that. We didn't use a graph. Yeah.
It looks like the graph that is making.
I know, yeah, that's a little confusing. Yes.
Okay. So, yeah. Wait. Go ahead.
Yeah. So one question about this like diagram is like, are you trying to filter out those features which are, I mean, they don't have that much of temporal information in it? Like, are you like trying to remove those features, or are you just like giving less importance, like less weight to those kind of features? Like I'm kind of confused.
Okay, so I guess a little bit both. So I think for the lower level here is something you just described, like what if the region of interest move out of frame? So if you look at the output, the two dot here, by the way, the dot means a feature from the neighboring frame. It's kind of wiping out because we find maybe it's not very valuable temporal feature. And if you like at the top level, we only use the red dot here. So we don't use the entire feature map. We don't use that regions because that region could be pedestrian or vehicles versus the whole features, including, for instance, like vegetation or some other irrelevant things. So by doing that, the higher level will save us some computation, budget. The lower level, of course, we use fewer features for the final computation. That makes sense? Okay, thank you.
If there's no further questions, let's thank to Dr. Liu again and for the fantastic talk.
Thank you. Stop. Oh.
Just stop recording.
Oh, yes, stop.
已经 stop 了，
嗯
那就可以退出了。
Stop.